How is that totally different a shape, making this structure the most likely to affect?
The ring also includes the mean group, which...
Yeah. If we go back and look at our protein structure, we had those two angles which we could do bond rotations about, the Ramachandran angles, psi and phi, right? We can rotate about both of those. Can you rotate about it anymore? No. Because of the ring structure, we've prevented that rotation. Okay. Let's say to get to the final three-dimensional structure, we have to do a rotation there. I can't do it here because the ring prevents it. Okay. It's still going back to intermolecular forces, and it's still going back to structure. Okay. Are other answers valid? Yeah. Okay. I would argue that that one's the biggest or the best answer. But if you went through and explained tyrosine, tyrosine's not a good option because it's the biggest one. Okay, so the biggest one is now going to have, depending on where the structure is located, could potentially cause it to balloon out and it can't now fold properly. Histidine, also pretty large. We're also changing the reactivity out there. Serine is classified as which amino acid?
Polar uncharged. Or no, polar but uncharged.
Polar uncharged. Histidine
Basic.
is basic. We've changed the functional reactivity of the amino acid. Okay? That could have a very large effect. Tyrosine, we aren't changing it. Tyrosine is still polar neutral. Okay? Histidine is polar, but it's polar basic. Okay? So it's looking at each of those classifications and saying, okay, how are these things going to potentially affect the overall end result, which is this thing needs to fold up. Kind of make sense? So, what things could you write on it right out of the way, out of the gate? So, and I'll be kind of obnoxious. We can erase all of your possible answer choices.
The left side is energy.
Okay. We're moving up in energy. We're looking at an energy diagram. What's happening on the other axis? It gets all sorts of weird names associated with it. Okay. What would you tell me about this point and this point? Products and reactants. So if I'm moving left to right, what's happening? I'm moving from reactant to product, which is the progress of the reaction. Okay? So we could call this reaction progress. Okay? The description that is typically associated with it is not progress, but it's coordinate. Right? They're saying the exact same thing. The reaction is progressing left to right. What else could you tell me?
Activation energy.
Where's your activation energy?
Next to the arrow on the right.
Okay. Your activation energy is the difference in energy between the reactant and the product is down here. That has nothing to do with... Nope. Your difference, look where the purple arrow is. It has nothing to do with the product. I could erase the product entirely off of this. The product has no effect on that. So EA, or activation energy, goes up to the transition state, which we represent as the double dagger. Okay. What other information could you throw in here? This goes back to your 152 knowledge. And old me 151. We officially have the Gibbs free energy. The difference between the reactant and the product energy is your Gibbs free energy. It's the overall energy change for the reaction. Okay? It doesn't care how fast we get there, which is ultimately the top half. We don't care about the transition state because I may go up in energy there, but I also equally go down. So that's a net wash. Okay? So now it's going to come down to picking out those last two pieces, and those last two pieces are something that it seems to be, I'm one of the few people that really pushes labeling those last two pieces. So if we erased all of our lines, those last two lines, or erased all of the box information there, there's two more things that we could put in there. Okay. Our A and B, thermodynamics and kinetics. Thermodynamics is all about the energy difference between our reactants and products, which is Gibbs free energy. So this is thermodynamics down here. What's happening on the top half? Okay, the top half is all about how fast it goes. If I drop that line down, that transition state energy, the reaction goes faster. Well, that's speed. Speed is kinetics. Okay, so depending on what we are looking at within our individual reaction, we may want to know something about the speed or something about the energies. Okay. And I will admit, the next section that we look at is looking at kinetics. Everybody has a hard time with it. All right, so just kind of be aware of that. It's going to be a rough section. It's chapter 6. Okay, and we've already kind of done our talk on thermodynamics. Questions about any of that?
So because though, so when they change it, because of the way that it is, it's showing that it's an exothermic reaction.
I was about to ask that.
But would it be, if it was an endothermic, would that mean that then when it comes, it's not gonna come down, it's gonna,
So in this case, we're showing an exothermic reaction, okay, and that has to do, I'm going to have to clear everything, that has to do with how we calculate our delta G. Okay. Delta G is delta H minus T delta S, and one of the things that we talked about is most people tend to ignore delta S. Why? It's very, very small. So our delta G ends up, most cases, equaling our delta H. Okay. So we can then look at our delta H as roughly the same thing as our delta G, and in this case that's calculating the difference in the product energy, our final energy state, minus our reactant, our initial energy state. If we look at it as drawn, where is our product energy state? Lower than the reactant. Okay? That gives us some kind of relationship that some people can pick up on, so let's change that up and put a number to it. Give me a number for the product and the reactant that would match your statement of lower.
100 for the reactants and 50 for the products.
What do we get?
-50.
-50. What does it mean when we have a negative delta H? It's exothermic. How would it be positive? Well, for it to be positive, the product energy must be higher than the reactant energy. How would that change the curve? Okay. Is all of the information that we labeled still the same? Yeah. We're now shifting our focus on where we do our calculations, but it's exactly the same. Same labeling system that goes through with it. Okay. We now have an exothermic reaction. Yes. I'm going to pretend that I said endo. We would now have an endothermic reaction. Or I could say, what do you mean it's still exo? Make sense? Okay, how do we decide what our interactions are? Okay, you said London dispersion here. How did you determine London dispersion?
carbon-hydrogen bonding.
We have carbon-hydrogen bonds which are non-polar covalent. And on the other side we have carbon and hydrogen bonds which are non-polar covalent. The interaction between those two groups will by definition be London dispersion forces. Alright, next box over. This is going to generate hydrogen bonding. This one gets a little bit tricky. This one generates what force? dipole, dipole. We don't see hydrogen bonding coming directly out of that molecule because there's no hydrogen present on that molecule. But what happens when I now look at the interaction between those two groups? Now I have hydrogen bonding because the other group is supplying the hydrogen for the hydrogen bonding interaction. Okay. Make sense? And so that's our answer. Next one down, what do we have? Should jump right out of the page at you. You see a bunch of charged species. It's immediately ionic. Would be an acceptable answer. The other answer that I would accept would be electrostatic. I don't remember if we talked about it as electrostatic or as ionic. I think I just talked about it as ionic. Okay? Which again goes back to intermolecular forces. Right? Noticing some patterns here?
Forces are a big deal.
Forces are a really big deal. You're going to keep seeing them again and again and again. Okay? Being able to apply and understand them is pretty critical, in my opinion. Okay, so we've got histidine, and now we've got KIDS as our new amino acid. I did make kind of a mistake here in trying to classify, because you notice that we've got how many equivalence points? We've got 3 equivalence points. We've got 1, 2, come on, stupid pen, 2, 3 equivalence points, which means we will have 3 half equivalence points. And at our half equivalence point, what do we know? We know our pKa is equal to our pH, so at the half equivalence point 1, I have pKa 1. Then I have pKa 2. And I have pKa 3. Okay. The PI, how do we determine the PI? Average of 2 pKa's, there's 3 pKa's. So which 3 pKa's, or which of those 2 do you average?
You would have to know,
You have to know the
because
PK.
some of them are different. Some of them take PK1 and PK3.
What is the PI? So yes, why do they take different ones? What defines the PI?
It wasn't really a hard, fast rule.
And there is.
What's the part of the point where the charge is completely neutral?
That is the point. It is the point where your structure is neutral, period. That is it. Okay. So deciding where it is neutral then comes back to the structure and looking at the charges. This is where I goofed. We'd have to decide where our structure is. You'll notice that if we transition through this, we should end up with, let's see, I can do this. We would have some protonated state here, pXa. At the next point, what would we have? Px minus 1a, right? We've lost a hydrogen. At our next red point, what will we have? Hx minus 2a. And at our next point, we would have Hx minus 3a. Yeah? So that means how many hydrogens do we have?
3.
3. Okay, so we could go back through and change those x's to be our, whoops, a minus 3. This one becomes H2a. Whoops, not H2a. That was dumb. Sorry, I apologize. That becomes HA. The one below it becomes H2a. And the very first one is H3a, right? What charge? And I know I said minus 3 up at the top. But we got to watch out for that. What charge? depends on the reactivity of our group. If we're looking at an oxygen carrying the hydrogen, or if we're looking at a nitrogen carrying the hydrogen. You could attempt to make some kind of educated guesses on this. That's more than I want you to deal with. Okay? So, because that was a big mistake, let's fix this. Let's do that. These are now the labels that you would need to, did I do that right? Close enough, that'll work. We just remove that first one. What's our starting point? Oh, come on. Oh, now it just didn't. All right. What is H3A? Kids 2 plus. Okay, our fully protonated state, which I don't want to write that out, so I'm going to say E. What is H2A? Actually, I'm going to have to say the charge on it. H2A is D, which was +1. HA is our 0, which was C. And our last one is B at a -1. To determine the PI, it is the point at which I am at kid 0. Where am I at kid 0? C. I'm at this point. How do I determine that point? Curve wasn't drawn perfectly nicely here, but which 2 pKa should I average?
K and L.
What's that?
K and L.
I see your reference now. K and L, yes. pKa 2 and pKa 3 would get me my Ki. So I could also say that this is my Pi here. Okay? So I have a numerical value for the Pi, okay, by looking at those individual points. Kind of makes sense? And at this stage, I could then deal with F, G, H, and I. Okay? Those are points where? These are at our half equivalence points, which on color coding, whoops, was blue. Okay, at the appropriate ones. Remember, we got rid of kids -2. Does that make sense? So we slowly layer our information over the top depending on what we find most easiest. Look to me like you guys happen to be okay with the equivalence point, finding the half equivalence point, then it's a question of labeling everything else in there. Questions about it? Okay. Start getting really boring questions. Carbohydrates are polymers of monosaccharides. Where did this question come from? Our chapter 1 section. It's just kind of the general gist information. So you're getting a lot of just dumb memorization questions. Following is an example of a biological polymer. Okay? You may look at those and go, well, I don't recognize any of those names. Okay? You may not recognize most of those names, but you should be recognizing peptide is found in proteins. So for better or worse, the stupid naming of peptides for amino acids red flags it for being a biological polymer.
I was going to say Teflon, but that's not biological.
No, not at all. Which of the following is commonly found in prokaryotes and eukaryotes? This is again a chapter 1 question. I definitely glossed over it. No.
So none of them.
It's none of the above. Mitochondria are solely eukaryotes. Chloroplasts also solely eukaryotes, and the nucleus also solely eukaryotes. Prokaryotes can do sun capturing, but it's not in chloroplasts. They use, anybody remember? It's not a chloroplast. A chloroplast is membrane bound. So that's the big issue between prokaryotes and eukaryotes. Eukaryotes have membranes, or membrane bound organelles. Prokaryotes do not. Okay, so all 3 of those are membrane bound. True or false about the equation shown? ATP plus water goes to ADP plus phosphate plus H plus energy. Formation of ADP represents a catabolic process. What does catabolic mean? Okay. Catabolic means breaking down. So what I would write on the exam, because I can't ever keep these straight, as soon as I saw catabolic, I'd probably write breakdown, and then I would skip the question. Right? But go back and look at the equation. We're going from 2 molecules to 3 molecules. Is that a breakdown or a put together? That's breaking down. So is that true or false?
True.
True. Okay. Entropy decreases through the course of the reaction. This first one was true. What is entropy? Okay. So we can look at disorder. I think motion is easier to understand. This is ultimately up to you to decide. Where are you going to have more motion? On the side with 2 particles or the side with 3 particles? Side with 3. There is more motion on the product side. To calculate a change, it is products minus reactants. If there's more motion, pick a bigger number. 50 minus 1. What's the value? Positive 49. What happened to the entropy in the course of the reaction? It increased. What is this statement saying? Decreases. Which means false. Makes sense on the kind of step-throughs on each of those? Reaction is endothermic. Endothermic is referring to our energy, our delta H. Endothermic for a delta H would be positive, which means energy is
Consumed or used.
okay, consumed.
On the reactant side.
Okay, I would argue that instead of using consumed, you should specify which side of the reaction, reactant side. Okay, where is energy shown?
Product.
Which means
It's
it's exothermic. That statement is false. Spontaneous at all temperatures. Spontaneous is a question about Gibbs free energy. Delta G equals delta H minus T delta S. Delta H for this reaction was negative. Temperature for this reaction is, why'd you say positive? It is always positive because our temperature for delta G is in kelvins. It's always positive. What was our delta S? It was positive, which means our delta G is always negative, which means it is always spontaneous. So it's going to be spontaneous at all temperatures.
Wait, delta S?
Delta S is entropy.
Oh, entropy.
Right. So where this question is going to become particularly confusing is if you go back and process, where's my minus sign that I can't see? There it is. Okay. If you go back and start to use your true-false questions above, the true-false questions ask about entropy and enthalpy, which is changing the signs. So if you start to say some of those are true and they're false, you're going to start to use the wrong sign and it's going to build on you. Okay, make sense? Which of the following reactions represents the following equilibrium expression? To do equilibrium, what is it? How do you calculate it? Products over reactants. So without even looking at the answers, what you should immediately be doing would be taking that information and saying we're taking ADP plus P plus H plus, and we're going to ATP. Once you've got the equation, you just got to find the one that matches, okay, or that best matches. You'll notice that we don't get any one of them that exactly matches. What's the issue? Which is our closest match? E. What is the issue with E? Why does it not match perfectly? We have the water. Why did the water not show up in our equation? It's going to come back to 152 knowledge because I don't think we explicitly stated it in class.
That's part of your K value if it's K
Kw, water does not show up. So the reason why water disappears from our K expression is water is our solvent. Does the solvent concentration change much? No. So it is effectively a constant. So when we go through to solve for the constant, we're going to group all of our constants, including the concentration of water. So it is factored into our K expression already. Okay? So it's not that we're excluding it from our equation, it's that it's already there in our K value.
Don't only do that if it's KW, or
It is, so if you see water in a reaction, it is 99% of the time a solvent, which then means its concentration is 55 molar. You run a reaction, it will change. It'll change by a factor of 10 to the minus 3 on a big reaction. 55 versus 10 to the minus 3. Meh. Not a big enough deal. Example of hydrogen bonding, are we good on that? We're looking at which answer? All of the above are hydrogen bonding. A is your classic example of hydrogen bonding that we might expect to see in water. Okay, so that is valid, but when we move to B, what do we have? This is a dipole. Oh God, that says dipole. This also says dipole. So we have a dipole-dipole force. Within that dipole-dipole force, is there a hydrogen bound to oxygen, nitrogen, and fluorine? Yes. Okay. So that's where you have to be careful on your definition of what makes hydrogen bonding. Which of the following compounds will act as a hydrogen bond acceptor? To accept a hydrogen, what does it need to have? So the quick answer is electrons. Notice all but D have electrons. A hydrogen bond acceptor is not just an electron donor. It is an electron donor coming from oxygen, nitrogen, or fluorine, which means B and A are not correct answers. C is the only one. In the formation of a peptide bond, the alpha carboxyl carbon will need to act as. We're going to keep coming back to these definitions, particularly as we move through our glycolysis kind of stuff. Okay, so if we look at the end result, we are forming a bond between the nitrogen and the carbon. Which atom likely supplied the electrons to make that bond? Why the nitrogen? Yeah, that's getting back to the answer. But why would nitrogen be a good electron donor typically? So there's a good idea. Looking at it from the flip side, the oxygen is taking electrons away from the carbon, which means the carbon carries what charge? Positive. It's lost electrons to the carbon. If the carbon is positive, it must be acting as an electron acceptor, which is our electrophile. Whoops, did I do that right? Yeah, I did that right. Okay. If we looked at it the other way, between the nitrogen and the carbon, which one's more electronegative, nitrogen or carbon? Nitrogen, which means which one is more likely to be found with electrons? Nitrogen, which means the nitrogen is more likely to act as the donor of electrons. There's our nucleophile. So if the nitrogen's our nucleophile, the carbon had better be the electrophile. Okay? So we can process it from either end of that. What makes this one trickier is that when we look at our starting conditions, does the nitrogen look like a nucleophile? No. Because it has to go through a sequence of protonation and deprotonation steps. Okay? For it to act solely as an acid or a base, that had better be the only thing that happens, the exchange of a proton. That is not the only thing that happened here. Okay?